Hi class, we're going to go through lesson 3.6, which talks about linear inequalities. We're only going to have this lesson on video, so make sure that you're paying attention and you're taking notes. For lesson 3.6, we're going to talk about intervals in graphing, properties of inequalities, solving linear inequalities, and then solving compound inequalities. We're going to start with section 1, which is intervals and graphing, and follow along in your books on page 184 for me. Okay, so let's go ahead and get going. First thing we're going to talk about is intervals on the real number line. All right, so basically we've talked about inequalities before, and inequality is going to be basically anything that doesn't have an equal sign. So when you have something like an equation that looks a lot like an equation but just does not have that equal sign but has something else, that's going to be an inequality. All right, we're talking about algebraic inequalities in this case. And in algebraic inequalities, algebra obviously means that you're dealing with symbols, so symbols that represent a number or represent a value but are not actually written as a number or value, something like x. And then inequalities is going to be anything that does not have an equal sign. So here we have some examples of some algebraic inequalities. We have x is less than or equal to 4, x is greater than or equal to -3, x plus 2 is less than 7, and 4x minus 6 is less than 3x plus 8. So these are all examples of algebraic inequalities. Now, if you remember, this little line underneath that caret is going to tell you or equal to. Okay, so this statement is x is less than or equal to 4. That means that x can be anything that is less than 4, whether that's negative a million, whether it's 0, whether it's 3.9999999, or it could be equal to 4. So x can be anything right up to and including 4. All right? So that's a little bit about algebraic inequalities. Let's talk about how to solve algebraic inequalities. Solving algebraic inequalities is pretty simple when you just think about the phrase, which solutions satisfy. Okay? So like how we were talking up here. If we have x is less than or equal to 4, a solution that satisfies this could be either -3, or it could be -20, or it could be 4, or it could be 0. It would satisfy this inequality up here because any of those numbers are less than or equal to 4. So if we look right here, I went ahead and I gave you guys two examples using the example that we had up here. So x plus 2 equals 7. That's an equality. Okay, equality. Why? Because it has an equal sign. What does that mean? That means x plus 2 equals 7. So if you were to solve for that, you would go ahead and do some algebra and figure out that x equals 5. The only thing that can make this equation true is 5, right? And that's what you have to think about when you're thinking about inequalities, just as you do when you think about equalities, is you have to find all of the values of x that make the statement true. So in this case, x plus 2 is less than 7. You have to find all the numbers that keep the left side. Okay, it's not always going to be the left side, but in this case, it's the left side, basically the other side of the inequality symbol that keeps the left side or the other side of the inequality symbol under 7. So what makes this statement true? A couple of different things could make it true. 1 could make it true, right? Because 1 plus 2 is still less than 7. 1 plus 2 equals 3, and then 3 is less than 7. So that's actually an answer to this inequality. And that kind of brings us to the point where we realize that inequalities are, for most of the time, going to have multiple answers, okay? Unless it's a bounded inequality, it's almost always going to have multiple answers. But even bounded inequalities will have multiple answers. And we're going to talk about what bounded and unbounded is. 2 is also a solution. 3 is also a solution. 4 is also a solution, right? 4 plus 2 equals 6, and that's less than 7. -38 is a solution. 0 is a solution. -a million is also a solution, okay? Basically, what keeps this statement true? That's what you have to think about, all right? Once we solve inequalities, we also have to try to graph them, okay? The best way to represent an inequality is through a graph. Okay, I'm going to go ahead and move this up. All right, what does it mean to graph an inequality? Basically, to plot solution sets on a number line. Whenever you plot a solution set's just going to be the possible answers that it could be, you plotting an interval. Okay, an interval is going to be either unbounded or bounded. Now, what does that mean? Before we get into that, let's talk a little bit about graphing. I have two examples here for you guys. One of them is x is greater than 7, and the other one is x is greater than or equal to 7. I went ahead and I graphed them on these two sticky notes here. X is greater than 7 tells me that the x value, whatever it may be, is going to have to be bigger than 7. It could be 7.1 or it could be 532. All right? We don't know what that x is going to be, but in this case, to be able to graph it, we have to use something called a parentheses. In math, parentheses, obviously, we use those all the time, but when we're graphing, we use this parentheses on the number line to represent that your x is going to be everything that is greater than 7, not including 7. That means whenever you're using a parentheses, you're only going to use parentheses when you have a greater than or less than symbol, not when you have an equal symbol there, okay? All right? Whenever we have parentheses, we call that an open set or an open interval, which means everything right up to this number. So 7.1 or 7.000001, that can all go all the way up to 7, but it cannot include 7. Parentheses does not include. But in this case, we have x is greater than or equal to 7, in which case we use a bracket. Now, a bracket means that it is a closed interval. Now, that means that it does include 7. So the answer to this, to x, could be 7, 7.1, 7.2, 800. All right? Anything that is greater than or equal to 7 is going to be an answer, a possible answer for x, okay? Now, a good way to remember this is by just thinking about the term flat. A bracket is going to be flat, right? It's not rounded like a parentheses, right? And when we talk about flat, we say in 3 minutes flat, right? Or $500 flat, something flat. What does that mean? That means it's exactly that value, okay? Nothing more, nothing less. So if it's flat, it's going to be a bracket. That means it includes that value in that, okay? So that's just a quick thing about how to use parentheses and brackets, because we're going to talk about that now that we're talking about bounded and unbounded intervals. So when we're plotting solution sets on the number line, we said they could be bounded, they can be unbounded. Now you can use parentheses or brackets in both unbounded and in bounded intervals. Now the difference between unbounded and bounded is that you're going to be using these things right here: infinity and negative infinity, okay? That little sideways A stands for infinity. Now, what does that mean? That means that your interval is going to go on forever in one direction. Let's go back to this right here. These are both unbounded intervals. Why? Because we're stopping at 7 on one side, right? But we're going on forever in this direction, in the positive direction. That means that x on this number line can be everything right up to 7 in the left direction, but then can go on forever in the right direction, okay? It can go up to 1 billion. X can be 1 billion in this case. Whereas in a bounded interval, you're going to basically have a set that is trapped within endpoints, okay? It's going to be closed off. That means that your x is going to be between two different values. It's going to be finite, okay? An unbounded interval is going to be infinite, so it can go on in either direction. Now, I want to show you in the book, really quickly, it talks a little bit about bounded and unbounded intervals. So if we look right here, an unbounded interval on the real number line, all right? So if you let A and B be real numbers, the following intervals on the real number line are called unbounded intervals. Okay, in this case, if you have a bracket, A, comma, infinity, that's the notation. That's actually how we're going to be answering these questions when we're solving them. Okay, not so much when we're graphing them. The graph looks like this. You're going to have a bracket on A. Why? Because the bracket means that it is or equal to A, and it's going to go on forever in the infinite direction. Okay, we're going to touch on this more in the next video, but just so you guys know, unbounded intervals are going to go on forever in one direction. It can include brackets or it can include parentheses. One thing to note, whenever you have infinity, you will only ever put infinity in a parentheses. Why? Because you can never actually get to the value of infinity, right? Remember that we use parentheses to talk about values that we are not including. You can never actually get infinity, therefore you can't include infinity, okay? So just remember that, parentheses for infinity, always. And then over here, if we're talking about bounded intervals, here you have pretty much a better example, okay? If you have an inequality like a is less than or equal to x, which is less than or equal to b, that just means that a is going to be your endpoint on the left, and b is going to be your endpoint on the right, okay? Now, all that means is that this is going to be a closed interval. It uses brackets, and it is also going to be a bounded interval. Bounded intervals are going to be trapped within two endpoints. Now, we're going to do some examples, and this will make probably a little bit of better sense, but make sure that you read this and that you read the unbounded interval explanation as well, okay? So moving on to the next video, we're going to do some examples.